It's a pleasure to be here. This is my. I was just saying thank you so much for the introduction, Ryan. It's a pleasure to be here. This is my second time lecturing at WPI. Last course that that Raha took, we had a similar lecture there, but obviously with a different theme. I make sure to not repeat my themes as I go from one lecture to the next because there's just so much happening in the field, and I wanted to share something relevant and something that has an area that's picked up a lot of momentum. And RL, as I was mentioning earlier, is an area that's pretty hot right now in the field. A lot of labs are doubling down on it and trying to scale RL to come up with better models, right? So the focus for today is going to be agentic RL. So we're going to talk about how to utilize, RL as a beast, right? And build better agents with RL, right? And also incorporate things like responsible agents and align agents, right? So that's going to be a key area too, as we cover various parts of what it means to do agentic reinforcement learning. So on the right, you'll see this particular slide, you'll see the lecture agenda. And if we go clockwise, starting from foundations of agents, you'll see all of the various topics that we're going to cover today, right? So we'll start with the foundations. I'll cover the basics of what it means to be an agent or to create an agent. Then we'll talk about a very important question. We were in the land of SFT earlier, supervised fine tuning. But why have things changed? Why do we need RL in the first place, right? Why not carry on with, fine tuning that we've always done for the last couple of years? It's been quite the rage, and we've used it in a lot of different applications and scenarios. So what has changed? So that's going to be the next question we're looking to seek an answer to. Once we're done with that, we're going to talk about the entire journey of utilizing reinforcement learning with today's generative AI models. So the first step, right, to step zero is essentially imitation learning as part of that whole process, right? So we'll cover imitation learning, and we'll talk about why that is needed, and how does that help create better RL models. So the warm start component of the entire RL process, which involves imitation learning, that's what we're going to cover. And once we're done with that, we're going to then start digging into core reinforcement learning. I'm going to give you guys, some basic overview of RL. We'll talk about policy optimization and preference optimization, which is essentially policy optimization, but in the domain of generative AI models like LLMs. So we'll touch upon, these three key areas: basics, policy, and preference optimization. And now that, at this point we'd have the stage set up, with basics of RL, we'll then start moving on to applying RL. The next step would be to cover RL for tool calling agents, which is a very common use case right now. How do you teach a model to call tools, right, in the form of APIs, in the form of MCP servers, which are also again very popular. The MCP protocol, is ubiquitous at this point when it comes to having a model like an LLM be able to call an external tool, like look up Slack message, or connect to your Google Drive or OneDrive, Microsoft OneDrive, and just generally connect with anything externally, right? So tool calling is pretty important. It gives the LLM a lot of abilities beyond what it's inherently good at. As part of this discussion, we'll also cover reward modeling. How do we come up with a reward function for better tool calling? And then we'll move over to RL for computer use. How do you get RL to to basically adapt a model to be able to do a whole bunch of tasks, with GUIs and, say a browser, or in fact any other, application on your computer, right? How do you automate that? By having the model learn nuances of, various tasks and steps, needed to, achieve that particular end goal or task. So we'll talk about that. We'll discuss how to create or how do you model the reward function for this particular use case for computer use. And then we'll start heading into responsible agents, which is very aligned with the theme of this course. Because responsible AI is obviously huge, and deploying a very powerful technology like this, obviously, discussion on that would be incomplete without talking about responsible deployments. So we'll be touching on responsible agents and RL for aligned behavior. And then once we've got all of these different areas covered, we're going to talk about evaluation. How do we figure out if a particular model that has gone through RL is performing well enough, right? How do we figure out if it's doing well from a performance perspective, it's doing well from a safety perspective? And even if it's a chatbot, for example, right? Multi-turn chatbot, how do we ensure success there? So the evaluation piece is going to be key, and we'll touch upon that. And then finally, we'll wrap up covering I'll offer some more pointers for you guys to dig further into if you guys are interested or want to learn next level detail for any of these topics. So that's how we're going to structure today's talk. And with that, I'll get started with the foundations of agents. So this slide basically covers at a top level what it means to for an LLM to behave as an agent, right? And what is the key distinguishing factor? So on the right, you'll see a diagram which basically illustrates the core, the LLM at the very center. That's called the agent core. But there's a whole bunch of different components around the agent core that come together and create this whole package, which is, an agent, right? And this is precisely, how you define an agent, right? An LLM core surrounded by various different components like memory, like planning, like tools. And then basically with the user requests coming in, the LLM basically utilizes memory to look at prior interactions, for example, or even prior outputs that is generated, not just prior inputs, and comes up with a plan which basically addresses the user query or a request that has come in. And as part of addressing the query or carrying out, coming up with a response for that query, it uses certain tools. And these are the three key components that we typically see, right? Memory, planning, and tools. And that packaged together with a base model, an LLM model, which is basically at the heart of everything, literally at the center, which is the agent core, is what constitutes an agent, right? That's the typical end-to-end agent pipeline that we typically see in the field. And a quick nuance is the tools can be in various different forms, but ultimately we model everything as an API call. So you could underneath, under the hood of an API call, you could have implemented things as as an MCP server. You could have implemented things as something that initiates a sequence, of actions, calls the Python interpreter, for example, or does a web search, for example, could do it locally, could initiate brand new sandbox, right? Which is how a lot of these, frontier labs do it, right? So if you say require a web search, right, to get a query answer from ChatGPT or Claude, it's going to create basically, a sandbox that carries out a web search, and then you can do a lot of follow-up action through, follow-up queries in a multi-turn setting by having it modify the query in certain ways and look for something else and look for two different things and amalgamate the output together to get you a good response. So a lot of that processing happens, thanks to the intelligence layer that an LLM offers, but it does utilize memory planning and tools to be able to carry out the desired task and take action in a lot of cases. So it goes, web search is illustrative, but it can go way beyond that and modify state on your local computer, for example, and take actions on behalf of you. So this is an agentic flow at a top level. Now, next up, we're going to dig into why we need RL, and why can't we be happy with just SFT, right? Supervised fine tuning, which is how we've been, domain adapting a whole bunch of these base models, right? So say take an instruct model, you apply SFT and you're able to have it learn, something that has not come up earlier, during pre-training. So, we've had that paradigm of transfer learning for a while. But the challenge here is that SFT essentially is a way to do imitate races, right, without learning the consequences of actions, right? So if you think about SFT, it is essentially categorical cross entropy loss on the next token, and all it does is basically teaches the model to prefer certain tokens given a particular sequence of input, right? The prior sequence that it has, which includes the prompt as well as tokens that it's generated, right? The entire sequence, given that, conditioned on that, increase the probability of, the next token based on ground truth, right? So that is the entire idea behind SFT. But that basically means models can't, perform trial and error and can't thereby learn consequences of their actions, right? And this basically is a big limitation because this means models can't learn, when tool use is required or, good to have or a must have, right? There is no distinction between the two that the models learn easily. But with RL, the entire framework is structured as such where this learning is imparted inherently as part of that process, right? Because it is based on the concept of trial and error, right? So model interacts with the environment and gets a reward in return and a next state, which is next token in return. But the challenge here is that SFT has no such notion, right? So it'll only basically do something called as imitation learning, which we'll cover in one of the coming slides, and teaches the model to perform tool use in a particular scenario, but it does not teach a model to not do or not utilize a particular tool. So in a different scenario, which essentially means the model is limited in its learning. Um, and also, there's also the trade-offs between multiple different tools, especially if you've got a repository of tools, which is commonly the case in the industry where we need a model to carry out a whole bunch of different things. And it does have all of the capabilities, but at runtime, we basically fetch the relevant tools based on a particular query within the prompt, and then have the model choose between those tools, right? Um, the challenge is, more the number of tools, more the nuances that the model needs to understand. What are the boundaries between certain tools? When do you choose one versus the other? What is that black and white area, right? All of that has to be really crisp and clear. Otherwise, the model's going to end up calling tools, a little bit randomly, right? So these demonstrations, SFT demonstrations, don't really teach the trade-offs between multiple tools. They give you essentially you've got ground truth, and you teach the model to prefer a particular tool in a particular scenario without telling it what other options it has and what would happen as a consequence if it were to invoke a different tool in this particular context, right? Imagine a scenario where a model has to call one tool to achieve something, but there could also be a parallel scenario where a model could call a couple of different tools and then give you the same end result, right? Now, if you favor lower latency, which we should, and when we talk about remote modeling, I'll talk about that in a bit, where RL is able to, also have a model learn the most efficient way to carry out a certain task. In this case, it would be just invoking one tool, assuming it's lower latency than invoking two tools in succession. But obviously there's nuances that the two tools could also be called parallelly and could probably take lesser time than one tool. There's also all these edge cases, but the model doesn't learn any of these different alternatives and options because it doesn't try out different options and seeks a reward in return, which is the case with RL, but not as much the case with SFT. Now, SFT, the other thing is that it doesn't look at execution success. There's no tool outputs and environment signals. You could structure the entire pipeline to look at execution success and return back the tool output and all of that, but it doesn't use that as part of the learning process, right? There is no feedback that gets utilized for the model to choose tools better. In RL, this is typically the case. And the other thing is, the with SFT, teaching a model stopping conditions or workflows that are very dynamic, where, like I was mentioning earlier, think of tool calling as a graph, right? Where you could have multiple nodes being explored in parallel. In some cases, they converge to the same node, and there could be an inherent dependency graph between tools as well, right? Where the output of one tool feeds to the input of another. So all of those nuances have to be taken care of, and RL is well positioned to have the model pick up on these nuances, whereas SFT basically teaches one way to achieve the desired end result, thereby limiting the learning signal, in case of SFT versus RL. So these are some of the key areas, key reasons why the field has started exploring RL for things like tool calling for agents or generally for agents, and why there are inherent limitations to how we were doing this earlier with prompt engineering and SFT prior to that, where we teach the model, the nuances of tool calling, and then engineer the prompt in a way where it picks up on samples and inputs and the tools that it needs to call with, say, few shot examples. And you could also include samples where it should not be calling tools, right? So you could structure a great prompt, but there's going to be inherent limitations to that pipeline. So these are the reasons why we've moved and evolved beyond that. All right. Now here's the flip side. Why do we need RL, right? And I gave a quick preview of some of those ideas in the prior slide, but just to cover those explicitly here. With RL, the beauty is that you can come up with a reward function that could be granular. It could be coarse, it could be granular, and we'll talk about process versus outcome-based reward modeling. So it's all totally up to the practitioner, right? How they structure the reward model, and you could reward an LM for small steps that it's taking along the way as it achieves the desired end result. That becomes process modeling versus the final outcome, right? So there's many ways to structure it. There's a couple of ways to structure it is what I'm saying, and ultimately, the job of RL is to basically maximize the cumulative rewards, which is the return in technical RL terms. And as part of that journey, as part of this, objective maximization, which is typically implemented in code as minimizing the negative of the objective as a model as a loss function, which is how we typically run the optimization loop for any model training, right? We minimize the loss, so you just flip the sign and then you minimize the negative of the objective, which was to be maximized earlier. But keeping that implementation detail aside, once you're done with this, optimization step, right? I'm assuming we're using algorithms that depend on, policy gradient, for example, and we'll touch upon that. Most of the, algorithms that we use right now for RL do have some of that flavor, right? Where we are basically coming with a gradient of the loss function, as is typically seen with deep learning model training. And we're trying to minimize that loss function, right, by taking the gradient of the loss with respect to the weights, and updating parameters iteratively, step by step, right? So it's a very similar loop with RL. The only difference is the objective, right, which is maximizing the cumulative rewards, like I've mentioned here. But once you're done with that, the idea is that this encourages the model, the underlying model, to take correct trajectories, correct steps along trajectories, and improve efficiency. And because you've encouraged the model to take small mini steps along the way, if you're doing, say, process-based modeling, and where you're assigning a reward for each small step, a positive reward for each small step that the model is taking, the model learns over time, over a bunch of different RL episodes or trajectories. It figures out that it needs to carry out a task in a particular way, right? So that's the entire learning process. That's the outcome optimization piece. And the good part about RL is, and this is a big point, is with SFT at runtime, if the distribution of the inputs is a little different than what it was, trained on or SFT'd on, the challenge is that SFT doesn't scale well out of distribution. And this is a big, key piece, especially as models get deployed in the industry, because there is typically a distribution shift that we encounter as models get deployed in production. There are new use cases coming in. There are new kinds of user queries coming in because of a whole bunch of different other components in the pipeline, that are undergoing a change. It could even be a different feature that was added for, say, a particular, system that was deployed, and that caused, a kind of feedback loop into a different feature. So there is a distribution shift over time that we see. Now, SFT doesn't do well with that. There is typically an out of distribution impact that we see. But with RL, because the entire strategy is you know, you know, adapting a model is based on discovery, right? Based on exploration versus exploitation in a way where it needs to try out certain tools, if it's a tool calling use case, and it needs to, you know, utilize some of its prior learnings in certain other ways, in certain other instances, if it's doing more of, you know, exploitation versus exploration. This strategy works out pretty well for out of distribution use cases. So that's one of the superpowers that RL has. Um, and then, you know, finally, you know, with rewards, like I mentioned earlier, there's many ways to structure rewards, and we'll touch upon a whole bunch of that for different use cases, right, from tool calling to computer use. But it depends on what granularity you're structuring or shaping your reward at, right? Do you, you know, assign a reward for small steps that the model is taking, or are you only assigning a reward, say one or zero, based on the outcome, based on the final result, right? So DeepSeek R1, for example, looked at both process and outcome-based rewards. But you know, the easiest implementation that we've seen in the field for, you know, any kind of reasoning model, you know, DeepSeek R1 is a good example. But you know, the based on the final output of a particular piece of code that the model generated, that did it work, did it run? You know, and was there, you know, correctness in the form of formatting? Was there, you know, a latency, you know, concern there? You know, one generation versus another. In which case, you know, if you structure a reward function with these components, you can teach a model to write better code, right? By write code that's functional, write code that's better formatted or structured, right? Code that does not take an inefficient route to achieve an end result, right? So that's the latency part that I talked about. So, you know, the when, which, and how that I mentioned on this slide here, we'll touch upon that in a lot more detail, so don't worry about it. But it's a framework that, you know, I've developed, which basically for tool calling is this is how I tend to structure things when I'm, you know, structuring my reward function, which is a way to signal to the model as part of the RL loop to understand when to call a function, because in some cases you do not want to call a function, right? And you know, which is the essentially the function that needs to be called, which function to call, and the how is essentially the arguments that need to be, you know, put together to be able to create a function call. So that's the framework, and we'll touch upon more of that in later slides. Um, Now, the other thing is, as far as new tools are concerned, you know, and you know, environments, RL scales pretty well. You can introduce new tools, and you can run a couple of more episodes with a new tool that you recently added, and have the model learn to pick up on that. And then finally, there's also multi-objective control, and this is pretty similar to what I was mentioning earlier with generating better code with, you know, reasoning models, which is what DeepSeek R1 did. You could have various different components, right, within the reward function. So you can reward the model for better syntax or better formatting. You can reward the model for execution, which is another word for latency or efficient code here. And then you can obviously, with any process based reward model, we also typically have an outcome based component, which is in this case the final answer. When you run the code, what is your final answer versus what is the ground truth if you were to run you know, a piece of code that answers the same query, you know, in a Python interpreter session, what would that yield? So there's multiple different components to the objective that we can introduce. And this is the entire, like I said, magic of RL. You can shape the reward function based on what you want the model to be great at. And by the way, each of these components can have different weights. So you could basically really want the model to generate great syntax, but the other components don't matter to you as much. That could be the case, right? Think of business needs, right? In the industry, especially, there's some certain things that, you know, we really value. In which case, then we need to increase the weight. But you could also have equal weights being distributed across all of the different components, right? So there's many ways. There's no one set way to structure a reward function. And keep in mind, the reward function is essentially the heart of the training process, essentially, you know, the loss function, right? So in deep learning or machine learning terms. So this is a core key piece of any RL pipeline. All right. And Ra, if you can just keep tabs on time, I don't see the watch here on my screen, but let me know if you're running out of time or anything, I want to make sure there's last 10 minutes for questions. But as
Absolutely.
you can see,
We
this.
have about 30 minutes left.
Okay, perfect. Okay. I'll have to breeze through stuff though if it's just 30 minutes because we have a lot of stuff to cover. But let me race right ahead. Um, so next step is why is imitation learning required before RL? Imitation learning is essentially SFT done in a warm-up fashion, right before we start implementing RL. And this is not absolutely required. With DeepSeek R1, the paper basically proposed two different models, DeepSeek R1 and DeepSeek R1 Zero. The R1 Zero variant did not use any form of SFT. It was purely trained with RL. But there's challenges there, right? Which is what the slide is trying to indicate, right? Why do you have one versus the other? Especially when there is a possibility of using just RL. So the idea is that, with SFT, you give the model a certain nudge in the beginning before you start introducing RL, where you teach it, certain tool called formats, teach it proper JSON structure by fine tuning it with SFT, and being able to show what an output JSON should be given a particular input. And if you're obviously with tool calls you want to also show it some examples where this arguments being constructed in various different ways for a particular API. You can show it overloading of APIs and a lot of those different nuances. So there's a lot of signal that we can offer during the SFT stage, and it's used to warm up the model to show it that there are to give it a rough structure of what's possible. And these preliminary patterns basically teach the model when to call certain tools and which tools to call and how do you shape the arguments for those tools. And once the model has picked up on some preliminary pattern, RL becomes a little easier, right? With DeepSeek R10 in particular, the paper basically said that if you do not carry out RL, there's a lot of language mixing that they see, and malformed outputs essentially, because there isn't a warm up starting point, right? So they actually call it cold start, SFT in the paper. But the idea is basically imitation learning. It's a different term for the same idea. In RL context, this is called imitation learning. But this helps, give that head start to the model before you actually start carrying out RL, right? So this is typically step zero. So if you go through a whole bunch of papers, in RL, and I have a lot of them linked later in the lecture, you'll see that this is a common step right now in the field. Now, why do you want to, what does this teach to the model, right? When you carry out imitation learning, this essentially provides good examples of valid API calls, and agent basically learns consistent structure for, in terms of when and how to call tools. It doesn't let the model obviously learn, in a trial and error fashion and get a reward in return. That's the entire framework of RL, right? But none of that happens at this stage. This is just the warm-up stage. And you could also expose the model to multi-step reasoning traces, and which basically helps it decompose a problem statement into various different latent or intermediate steps. And this basically, like I mentioned earlier, provides a nice starting point for the model upon which we typically carry out RL with an algorithm like PPO or GRPO, and we'll touch upon some of that as well later, which to use when, for example, and what are the benefits of, say, GRPO versus PPO. But all of that comes later. The policy optimization step, PPO is proximal policy optimization, GRPO is group relative policy optimization. These are core preference optimization, RL-based preference optimization algorithms that we'll touch upon later. But these come right after, is what I wanted to showcase. SFT or imitation learning is a prerequisite step. Now let's start covering the basics of RL, and then we'll start jumping into the core of today's lecture. So there's the agent environment loop. On the right, you'll see the diagram. Agent, in this case, is the LLM, and it interacts with the environment and basically carries out an action, AT, and returns, the environment returns, a reward. It's actually returned by the reward model within the environment. So there's a dedicated model, could even be a reward function, doesn't have to be a neural model. Depends on how you shape it. And, we'll touch upon two different methods. DeepSeek R1, for example, used objectively verifiable reward functions rather than a core neural reward model. to prevent, reward hacking. But there's a couple of ways to do it. You can create a function, you can create, could just be a mathematical function, but you can also create a reward model. So that's RFT, and that basically returns, the next state to the agent. So this is how reinforcement learning, is typically structured. And the idea is that the agent seeks to learn a policy, which is basically the action, most optimal action to take based on the given state, which maximizes the probability of cumulative reward. So that's the equation you see on the bottom right. Reward getting added up over time with a discount factor gamma, and then you maximize the expected value of that over all of these different steps. So that's reinforcement learning. Now let's talk about policy optimization. Now, policy optimization basically, it's a framework of basically mapping states to action probabilities. That is the policy. And what we're looking to do in this framework is obviously to optimize the policy, right? And the policy is essentially a way of defining how the agent behaves as it takes different decisions as part of, a longitudinal process with various different steps in between the input and the output, right? So a policy model essentially, to take a step back, there's a bunch of different models that get utilized as part of any RL framework, right? Like we discussed earlier, within the environment, like I was mentioning earlier, you've got a reward model, right? But there's much more than a reward model. There's a reference model, there's a value model, and a reward model, right? And the policy model, which is the fourth model, is essentially the agent. The policy model is the core LLM, right? So this is a model that generates actions or text. If it's a text-only LLM. And the idea is that each of its tokens stacked together, right? Those they need to maximize the expected cumulative reward over time using RL. So that is the policy model. But there's a whole bunch of different models, and just to cover them quickly one by one. The reference model that we use in policy optimization, that is a frozen baseline, of the policy model. So it's literally a copy of the policy model right after the imitation learning step that we just talked about, which is right before the actual RL loop that runs, right? Like I said, the imitation learning step is just a prerequisite. Now, at that step, we make a copy of the LLM, the policy model, and that is just used to make sure that we don't diverge from this particular model too much as we carry out RL. And the main reason for that is just to ensure stability. RL is a very, it's a difficult beast to master, so there's a lot of stability concerns typically during training. That's common, and this is one way to address that. Um, and then finally, what we do is we basically utilize a policy gradient algorithm, which is one type of an RL algorithm, which adjusts model parameters to increase expected reward from sample trajectories. Very similar to how we carry out, gradient descent with, any kind of deep learning, model, and even with ML model, same framework. And the idea is to minimize the loss. In this case, the idea is to increase the expected reward. Um, and then we've also got the value model as part of the environment, and the job of the value model is to predict the expected return. And this helps us form something called as an advantage, which is the advantage of a particular action, how good a particular action is in a certain state to take, and what would be the relative benefit of taking that action in terms of reward compared to, a baseline, right, across all of the different actions that can be taken at a particular step. So the prediction of that expected return is done by the value model. Reward model, on the other hand, which is the last model that is utilized as part of policy optimization, basically, does not make a prediction, but it actually, comes up with the observed reward, and emits essentially a scalar score, which is the reward. And this score is the representation of how good your response quality is, how good your particular output is preferred versus another. So that's the role of a reward model. The actual observed reward is what it emits out. The value model, in turn, also makes a scalar score, generates a scalar score output, but does that as a prediction. And they're both trained, reward models typically trained first with human preferences if you're doing preference optimization. And I'll touch upon that in the next slide. But the value model essentially learns to predict this reward over time And that is, these all of these four models, policy, reference, value, and reward, work hand in hand together to carry out RL. So as you can see, it's a pretty involved framework. There's a lot of different nuances and details to go over. And what complicates this further is that instead of using models for reward and value, you could utilize a function. So a mathematical function, right? So you could have value function, you could have reward function, and that's also a key area where we've seen a lot of good progress. In some cases, in some frameworks, you do not need a reward model. For example, with DPO, right? In case of uh, it also does not utilize a value model, DPO. But with GRPO, for example, you do not utilize a value model because you can just utilize group normalized series of values. So there's a lot of different nuances and details depending on what exact algorithm is that you're using. Um, but just to give you guys a top level idea, policy optimization has been in the field for quite a while. And then preference optimization, which is, the what has come up recently is essentially a way to utilize some of these fundamentals that we discussed, the policy optimization fundamentals, and adapt it for LLMs, right? So in this case, like I was mentioning earlier, as a policy model, that's your main LLM. The model function is your policy. And what you're doing is you're basically training a reward model. If say you're using proximal policy optimization, PPO. This was an algorithm proposed, by OpenAI in 2017 by John Schulman and others. And the idea is that you can train a reward model based on human preference data, based on data, offline data set where we basically learn, what kind of a response is preferred versus not for a particular input or a particular prompt. We can train a reward model from it, right? So that was one thing, and then basically there's a couple of different ways to anchor, the a training process. So you scale based constraints, for example, and then finally what you do is we typically train an actor and a critic. And an actor is basically the policy. It's another word for policy, and critic is the value model. These are trained hand in hand, and that basically carries out using the reward function. That this basically shapes up the entire RL training loop. And over time, as a model learns to optimize or increase the expected rewards, it's going to come up with responses that are better and aligned, and depending on what was encouraged as part of reward model training. Right, as part of that data set that was put together to train a reward model, it's going to learn to maximize that reward, right? So if your data set favored clarity, safety, usefulness, there's a very common framework from Anthropic 3H. It's helpful, harmless, and honest. You could have various different dimensions, right? Based on those dimensions, your model will perform better. So that's the entire idea behind preference optimization. And like I mentioned earlier, PPO, DPO, GRPO, these are three key algorithms that carry out preference optimization. There's a whole lot more right now. But these are the three key main ones, and we'll touch upon them in later slides. Just for a time check, how much time do we have? There's a lot of content, so
It's
wondering.
about like 15 to 18
Okay.
minutes.
Okay, perfect. Yeah, I think we'll be somewhere close to around 20 minutes, but hopefully we still have time later for questions, right, Ra?
Yeah, absolutely. Like even
Okay,
if we do 20 minutes, we still have like about 15 minutes for question and answer.
perfect. Okay, that's excellent. Um, all right, so PPO. Like I promised earlier, we're going to touch upon each of these quickly, and I've got PPO, DPO, and GRPO here. Those are the three key algorithms. GRPO is more recent, introduced late last year, by the DeepSeek math paper. The V2 of that paper just came out on the 27th of November. So literally last week. So a lot of activity in the field. GRPO is definitely there's a lot of merits to it, which is why it's popular. But let me touch upon PPO first, and then we'll roll over to the others. So PPO, the idea was to use a clipped policy ratio. Policy ratio is essentially the ratio of different probabilities for an LM to carry out, particular action. What is the probability of doing that in its current iteration as it's going RL versus what was the probability when it started off with the RL loop, right? So that's the policy ratio. PPO introduced the process of clipping this policy ratio to basically make sure that the updates to the policy ratio are within a certain region or a threshold. So it uses epsilon as basically a guiding, number. So you do, 1 minus epsilon, 1 plus epsilon, and basically check, make sure that your update to the policy ratio is confined within that range. And then you've got the KL penalty as well that I touched upon earlier, the divergence penalty, which makes sure that you don't diverge too much from your reference model. And just to improve stability. So there's a whole bunch of different components. So you'll see that in the loss function that I've included on the bottom right for PPO. So all of these components put together form the clipped surrogate loss. That's what PPO proposed. And the AT is basically the advantage, which is basically computed by looking at the value function and then subtracting, that by the reward. And all of that put together essentially helps form a loop called RLHF, which is reinforcement learning from human feedback. And that loop essentially uses PPO in a way where you could carry out policy optimization like PPO, adapt it for an LLM use case to have it generate outputs that are more tailored towards what's aligned, right, for humans. So that's RLHF. It's a framework that utilizes PPO and adapts PPO for an LLM use case. Now, DPO was proposed a couple of years ago by folks at Stanford, and the idea is that RL has a lot of challenges. So like I said, stability is the biggest challenge, and we have to carry a lot of these different components and terms, as you'll see in these equations, KL penalties, for example, and clipping, as in PPO. DPO basically said, why do that, right? Why use RL, right? Let's just utilize, we don't need an explicit reward function, and even a critic, right? We can just use the base model, as, a replacement for that. But note that because RL is not involved here, there is no concept of a reward and a critic. Internally, obviously, the model learns to maximize probabilities of tokens that it, based on the ground truth, based on the data set that you're looking to, align with. But the log probability differences are what are taken between different tokens, and that's essentially what DP uses. So it's binary cross entropy loss, and it doesn't need any form of RL. So that's direct preference optimization, DPO. I've included the loss function here at the bottom right. A GRPO is yet another proposal that came out, last year in November or so from DeepSeek Math. It basically, obviates the need for a critic entirely, and says instead of using a critic, why not just compute baselines from based on group normalization of different sampled outputs from an LLM by just sweeping things like the temperature for a given prompt. So, and one of the key motivations of GRPO is that, the fact that it still uses RL. And the biggest motivation here is that RL was found to be better performing. There's papers that established that DPO, even though it didn't use RL and was way more simplistic, it wasn't as performant as PPO. So GRPO is actually based on PPO and not DPO. So it still uses RL, but it gets rid of the critic entirely. And for computing rewards, while there's no value or critic model, for computing rewards, it just uses objectively viable, verifiable, signals, right? It looks for code correctness, code formatting, things that you can statically check. You don't need a neural model for that. So in that sense, GRPO really, simplified the pipeline. Now, as far as the compute implications are concerned, obviously with any RL technique, there is enough in terms of compute, especially as you're training a model or aligning a model, with RL, because as you can see in the diagram on the top right, there are a whole bunch of these different models that I was talking about. There's not one model that goes into the entire framework. So you've got your policy model, you've got your reference model, you've got your reward model, you've got your value model. There are four different models that need to be accommodated in VRAM. And that is obviously that means it's compute heavy. The stability is another concern. But DPO is a little lighter in that sense because there is no RL component. It's a framework that does not use RL. So those are some of the key trade-offs, yeah, with different preference optimization algorithms. Now we'll switch gears to tool calling, and we'll talk about, why we need tool calling and how do you carry out, a model to, how do you have a model carry out tool calling. So tool calling basically operates through, iterative decisions, right? Where you've given a model a particular prompt, and in certain cases, the model needs to decide that it wants to call a tool, and in the other cases, it doesn't need a tool, right? So that decision-making capability is what we want to introduce in the model. So, you could have a whole bunch of different tools. You could have millions of them. There's a paper called Gorilla from Berkeley that looked at, I believe hundreds of thousands of tools, and then being able to pull relative tools with a RAG-like framework into the prompt and then choose which one to call. So, you're not confined to, the simplistic case of just a couple of different tools. And there's also various ways to call tools, like I was mentioning earlier, parallel and multiple tools at once and multiple parallel tools as well. So a lot of different ways to structure it. There's a lot of different arguments to tools that you want the model to learn, a lot of different formats, API schemas. All of that has to be taught to the model, right? So that's a key way, and the some of the preference optimization algorithms that we discussed on the last side, PPO, DPO, GRPO, they were used for preference optimization up until, let's say, late last year. And then soon we realized with, DeepSeek R1 that you could utilize preference optimization, GRPO in particular, to teach a model how to reason. Now that went one step further, and evolving that idea basically became RL for tool calling, right? So you could use preference optimization to teach a model to call tools, right? And understand when and how and which tool to call. So that was the entire idea behind adapting, preference optimization for tool calling. And that led to the genesis of tool calling, RL for tool calling. Now let's look at a quick reward model scenario here. So on the right, you'll see that this is an example of a reward function, right, for tool calling. And you could have various forms of different reward components. You could have rule-based rewards, which is what DeepSeek R1 utilized, where it looked for certain signals within a model's output to understand deterministically if the model's doing the right thing, right? So you could, run a piece of code, for example, like I mentioned earlier, look at the output, compare them with a string match. All of that is doable, right? So that's rule-based rewards, the deterministic way of verifying correctness. You could have a learned neural model that is based on a data set that was created. And that makes it a learned or deterministic reward model. And the output's going to be a scalar reward, as is the case with any of these rewards, is a scalar value. So you could come up with a model like that, trained on certain preferences or certain data, and then outcomes, a reward at the output at a scalar value. Now you could also do an LLM as a judge or a generative reward model. So there's three different ways of and you can combine either or. You could have one or the other. You could have all three to structure a reward function. So there's a lot of flexibility, right? And each of these different paradigms can target different parts of the LLM's output. So on the right, you'll see that the when, which, how framework that I talked about. So this is something that I've structured. So the way I write my reward functions for RL is for tool calling is in this sense where you want to gather a signal to understand the when part is the one calling a tool when it's absolutely necessary. The which part is essentially which tool is the model selecting, and the how basically looks at the syntax, it looks at the execution speed, and the arguments, right? And then finally, you look at the outcome as well, right? The final output that was generated. All of that packaged together becomes your reward function, right? So you add term after term, component after component, and come up with the reward function. In this case, this is the one for tool calling, but we'll cover a couple of more different reward functions. Now, coming to RL for computer use agents, this is a very hot area right now. We want to use LLMs or multimodal LLMs rather to be able to carry out tasks on a local computer, in a sandbox environment hosted over the cloud, a lot of different ways. But the way models do it right now, a multimodal model would basically look at changes happening on the screen, and I'll talk about how it figures that out and uses that as signal to understand if it's carrying out a certain step correctly to achieve a desired end goal, right? So, for example, if you ask it to make a food delivery order, for example, or book a vacation rental, for example, all of that is doable. but it needs to have enough signal, right? Now the signals are going to be, if it's a web page, it's going to be HTML code. It could be a DOM structure, document object model, which basically is a nice tree-based hierarchy of what's happening in a particular web page within the browser. And if a button is clicked or not, for example, or if it's filling a certain field, it can, DOM structures are used very commonly for that. Now, if it's an application on your computer, then it could look at Windows UI automation. That's another library. Or, Apple has Mac, automation trees, AX trees is how they're called, commonly called. A lot of these libraries that give us enough signal to understand if what kind of UI elements exist on the screen, and selecting a particular element to filling a particular field, to clicking a drop down menu. All of that is doable by observing state through these different UI trees, what they're called. And the idea is that using that to form a reward function is the entire basis of computer use agents, right? So if you look at this, the next slide here, on the right, you'll see a reward function which basically utilizes different components. It looks at, the first component, for example, if you're navigating to a certain page, say to put out a food delivery order. Have you, put in the URL correctly? Have you, pressed, the go button, for example, in your browser? That is the navigation part, right? The first component in that equation, right? So a reward is accordingly assigned if the model did that right. Now there could be a whole bunch of different elements. Was the UI element correctly interacted with? There was a button indeed pressed. Was a form indeed filled? Um, if this led to creation of a file or an output, right? Could be an artifact. If you ran a summary report, in an application, you could look if a file was generated on your disk, right? So that's a file handling reward. There could be an outcome based reward as well, the overall outcome, right? What was the end result you were expecting, and did you achieve that? And then you could include also some penalty terms, right? Safety, for example. Were any violations carried out as it was doing this, right? Did it do something it should not have done? Did it carry out a financial transaction when it was clearly told to confirm with the user before it carries out a big transaction, right? That's a key question that comes up in these flows, right? So you introduce a penalty term for that. Last, you could introduce a penalty term for latency as well, right? So you do not encourage the model to carry out flows that take that are inefficient and take long enough to carry out the task, right? So that's latency. So the key idea here is that you can structure a reward function is very in different ways, and put in the components that matter to you, right? To make sure the model learns to prefer certain actions at any step that maximize these rewards versus others. Now, next up, we've got RL for aligned behavior. And I'm going to go through this real quick because at this point, we have all of the fundamentals we need to showcase what it means to create a responsible agent, right? So when you carry out preference optimization, the data set that you use, in the data set, if you've infused signals that make these agents, prefer, certain outputs over others, by being more helpful, and um, offering outputs that are harmless, for example. You at the end of the day, once you carry out RL, you have a model, an agent that will naturally be better, at some of these key areas, right? Because you've encouraged that by doing the RL rule. So that is a key part of what makes a responsible agent. But at the same time, in the reward function, if you introduce certain components that make the agent, prefer or disprefer a certain scenario by giving it a positive reward if it's doing something right, it's doing something responsible, versus giving it a very large negative reward if it's carrying out, say, a financial transaction, like I said earlier, whereas there's no confirmation that was given by the user, so it purchased a lot of things off of, say an online vendor, that would be irresponsible, right? And you could model the same framework in various different ways. It all depends on your reward function and, the data that is used under the hood to be able to carry out preference optimization. So depending on what you, encourage the model to do, it's going to pick up certain signals, and that is the entire framework of making agents more responsible. So some of the design principles in this case would be safety-centered objectives, shaping the reward function so it minimizes harmful actions. And, while it's maximizing rewards, that make it do the right thing. Policy optimization, obviously. So, I want to make sure that the data, like I spoke about earlier, has some of those signals where it prefers a certain output over another. And those outputs are tailored accordingly, right, to showcase the model that it really needs to be helpful in this case, but not helpful in another case where you're, say, asking the model to how to make a bomb, for example, right? That would be irresponsible. So, your data set needs to have some of those samples that showcase that. And so those are some of the key areas put together. But once you have a model trained, there's a whole lot of work that needs to go beyond a model too. You need to log and have some traceability and interpretability to understand in which scenarios is the model responsible versus what are the other corner case scenarios where the model isn't giving the intended output, right? Where there's bad feedback we're getting from the user. So some of that monitoring loop also needs to be set up with CloudWatch, from AWS, Grafana. We set up a whole lot of dashboards that give us some of the signal once a model is deployed in the wild. Um, and with that, one last topic I wanted to cover is was on evaluation. There's a whole lot of different components, that you need to evaluate, and evaluation is pretty complicated with, our agents because there's a lot of different capabilities that make a great agent, and so you need to evaluate, various bits and pieces. You need not just the overall task, right? So you could have task level metrics where there's multi-step workflows, and then you grade the output at each intermediate step. You could have diagnostics where, at each step you have enough visibility into the kind of decisions, the tool calls that were made, UI actions that were taken as the model carried out a particular, task. And as you change distributions, does the agent hold well? That's another thing. Out of distribution, like I was mentioning at the beginning of the lecture, SFT isn't very well suited for that, but RL typically performs better. So understanding that robustness under distribution shift is very important. um, the credit assignment is basically a way to is basically reward assignment. But how do you do that when you have a longitudinal task? We have agents that say, perform deep research and a whole bunch of other tasks for hours. How do you grade the success of this agent longitudinally, right, over so many different turns, thousands of turns, and figure out what the discount factor would be in RL to look at immediate rewards versus future rewards. There is a balance for that, which is called the discount factor. How do you assign rewards? How do you come up with a reward function that's very longitudinal? That's very difficult. It's one of the key areas of research in the field. And obviously human in the loop, right? For a task, for an agent, how do you come up with making sure there's human in that pipeline where they're looking into these intermediate steps as well as the final step in various different scenarios across various different inputs and making sure that there's correctness and intent alignment. So that's key. Safety, risk mitigation, and multi-turn behavior, those are key areas that we typically evaluate agents with. And this is typically to make sure that there is enough of a responsible deployment. So you want to make sure the safety guards are runtime, the model isn't carrying out, big, actions that, require prior human approval, right? Like I said, financial actions, for example, and there needs to be penalty-based safety rewards as well. So we talked about latency, we talked about safety. Those there could be a bunch of different components within your reward function that are based that assign a negative penalty or the negative reward, right? Essentially a penalty, to make sure the model is discouraged from carrying out certain actions, right? That shouldn't be calling unsafe tools, or going beyond the allowed UI boundaries if it's controlling, your computer. So those things have to be baked in as well. Long horizon oversight is similar to, temporal credit assignment, which we discussed earlier. That is a challenging area, subject of active research. And lastly, how do you have an agent learn to be robust under, the misexecuted steps or, changes last moment where there was an additional UI, box that showed up on your screen. How does it recover gracefully from it? That is key as well to attend to corner cases and out of distribution scenarios. So that's another key area where we do a lot of evaluation to make sure the agent scales in the field. And then lastly, I've got a whole bunch of different papers that have formed this lecture over time. There's policy optimization, there's reward and verify models for agents. There's a whole bunch of different work happening there. A lot of these papers are from the last 12 to 18 months or so. So this is a very active area of research, RL for agents. Um, and then papers for multi-agent workflows. How do you decompose a problem statement, come up with a multi-agent collaboration setup? There's a lot of different use cases that get enabled. Deep research, for example, is a very, a pretty good example of a multi-agent workflow where it has a lead agent and it spawns a whole bunch of different sub-agents. So that's a good example of a multi-agent workflow. And there's a whole bunch of different frameworks that let you set up multi-agent workflows as well, right? From, LangGraph, LangChain, Baby AGI, N8N, a lot of different options. And then embodied and open-ended agents. There's Voyager, there's Open Web Voyager as well, and Web Voyager. A lot of different agents where for computer use, for example. There's That's again a very active area, one that we touched upon in the lecture. And then there's also ways to carry out auto ML intertwined with ML agents. How do you come up with a framework that is autonomous in nature for a multi-agent scenario? So there's papers for that. There's a lot more papers for reasoning, tool calling, benchmarks and eval. Like I said, very key area of research. With the sheer increase in the amount of capability that these models have now, thanks to all these different training steps, right, from SFT to RL for tool calling, for computer use, and there is obviously there's a spike in the amount of papers for correspondingly the amount of papers for evaluation as well. Because with an increase in capability, you gotta also have mechanisms to be able to evaluate those capabilities, right? So there's so many new papers coming in every now and then, but I've listed some of the ones that I've personally enjoyed and reading, and they're pretty key in the field. So there's a whole bunch of those for benchmarking. And lastly, I also have a primer that I've written, which actually covers a whole bunch of what we discussed in a lot more detail. And this primer is tailored towards agentic RL. So it covers, the core of, a whole bunch of different papers in the field. Some of those that I just linked in the prior slides, and talks about how they come up with frameworks to, eke out, the max you can from the model by having it go through an RL loop in a bunch of different ways, do it more efficiently, and how do you shape up a reward function? A lot of different nuances here. Obviously, key is preference optimization that goes hand in hand, as we've seen that this is part of the RL loop. Earlier used for just preference optimization, now being scaled to RL for a whole bunch of different scenarios beyond preference optimization. So this is a very detailed primer I have for a whole bunch of different algorithms, and goes from, doesn't assume any major prior knowledge beyond LLMs. So, covers the background and then it goes into each algorithm in a detailed way and then compares all of them. Linked right below the GIF here. All right. I know there was a lot of stuff, but I'm glad we're at the end, so we have time for questions. But yeah, thank you so much for having me over, and I hope this was helpful. And feel free to ask away.
All right. Thank you so much, Aman, for the wonderful talk. I am going
Mhm.
to stop recording and then we are going to open the floor for questions.
Sounds
Uh,
good.
so, give